Hi, this is a video demonstrating and assessing the Aspen simulation for the select report for Group S. Firstly, for the assessment of the thermodynamic model, the MEF filter that was chosen was PETCHEM, as the VCM production process will need a petroleum-based equation of state property method due to the presence of many hydrocarbon compounds throughout the process. In comparison of the different property methods, the two most applicable that we have found are the Peng-Robinson or K-Solve methods. They're both similar in the fact that they're both used for gas processing and petrochemical applications. They're both also very suitable for high temperature and high pressure systems and can be used at a large range of pressures and temperatures. The major difference that we have found is that the Peng-Robinson method has been more advanced, able to handle polar components and non-ideal systems that the RK-Solve method cannot handle, hence making it the more viable option and the option that we have chosen. Now, looking at the assessment of the models of the different units, we can see that the direct chlorination oxychlorination reactors use R-stoic reactors, which take into consideration the different reactions in each of the reactors and the different conversions of ethylene or chlorine in each reactor. The furnace also uses an R-stoic model just because of the simplicity of the thermal cracking process. As for the specification of the three distillation columns, a DSTW model was used for all three distillation columns due to this being the only model in the columns section in Aspen to only require the specification of the condenser and reboiler pressures and separates in accordance with the boiling points of the components being separated, so the heavy and light keys. Now, for the description of the process, each unit will be assessed starting from the DC reactor and ending with the OC reactor. Looking at the DC reactor, we have a flow of 4.2 million kmols per year at 99.9% purity of ethylene and around 4 million kmols per year of chlorine at 99.5%, with operating conditions at 120 degrees C and 4 bars of pressure, and the main reaction side reaction occurring as shown. This gives an outlet of 448 kmols per hour of EDC exiting the reactor. Next, the caustic scrubber consists of 3 units in this Aspen simulation: a mixer to mix the sodium hydroxide solution with the EDC stream, a reactor operating at 38.5 degrees C and 1 atm to react the NaOH with the unwanted HCl, and a component splitter unit that acts as a scrubber's sieve to separate the NaCl formed and unreacted sodium hydroxide from the further purified EDC stream. This stream then flows through a flash drum operating at 38.5 degrees C and 1 bars of pressure. This separates the excess ethylene and purges it. Pump P101 then increases the pressure to 10 bars of pressure. This flows through to an adsorption column, which then strips the water from the stream to an EDC stream flowing at 799 kmols per hour at 98.7% purity. After going through M301, the pump P301 increases the pressure to 35 bars of pressure before entering the cracking unit, operating at 500 degrees C and 35 bars of pressure with a fractional conversion of 50% for EDC to form VCM. In the separation system, the operating pressure of each column is based on the hot and cold utilities available, hence the valves and compressors are used to get the inlet streams to that value of pressure. The first column separates the EDC from the VCM at 99.9% efficiency with an operating pressure of 27 and 28 bar, the condenser and reboiler respectively. The EDC is then separated in C302 and recycled into M301. The operating pressure here is 10 bars and 11 bars at the condenser and reboiler respectively. In C303, the VCM is separated from the HCl, and the HCl is recycled into the oxychlorination reactor. The VCM exits the bottom stream at a rate of 399.2 kilotons per year at a purity of 99.8%. The HCl recycle stream is recycled to an oxychlorination reactor operating at 305 degrees C at 4 bars of pressure, with the inlet and outlet streams shown in kmols per hour. It then goes through an EDC purification as stated before.
The following table shows the heat duty for multiple units in a PFD, ranging from highly endothermic pyrolysis reactor all the way to a highly exothermic distillation column. The following heat duties were then used in the pinch analysis to help us find the pinch point temperature in order for us to know how many and where to place our heat exchangers. Our calculations meant that we now needed 3 heat exchangers, 2 primarily found in the beginning of our process and 1 particularly around the distillation columns. This allowed hot streams to cool off colder streams rather than heating them up from the outlet temperature. Therefore, the energy consumption of our system is heavily decreased.